Dual Chunk Attention or DCA, enabling Llama 270B to support context windows of more than 100K tokens without continual training. Great paper, Training-Free Long Context Scaling of Large Language Models. Dual Chunk Attention, DCA, innovates by decomposing the attention mechanism into manageable chunks, allowing the model to maintain high performance over long text sequences without the computational burden of traditional methods. This chunk-based processing is divided into intra-chunk and inter-chunk attention, with a third type, successive chunk attention, specifically handling the transitions between consecutive chunks. The intra-chunk attention focuses within individual chunks, optimizing attention for shorter, contained sequences, thereby retaining the efficiency and accuracy in understanding local context. Inter-chunk attention extends this by allowing the model to reference and integrate information across different chunks, which is crucial for maintaining the coherence of longer passages. Here's how the intra-chunk attention works. With example, the long text is divided into smaller chunks, each with a specific size, s. For example, if the document is 12 words long and the chunk size is 6, you'll have 2 chunks, each containing 6 words. Then comes positional encoding. Each word in the text has a positional encoding that tells the model its location. In intra-chunk attention, the positional encoding is adjusted to be relative to the start of the chunk. So, the first word in each chunk will have a position of 0, the second word a position of 1, and so on. This helps the model focus on the relative positions of words within the chunk rather than their absolute positions in the entire document. And then finally, the attention calculation. The model calculates attention scores between each pair of words within the chunk. These scores indicate how much each word should pay attention to other words in the context of understanding the meaning of the chunk. By combining these attention mechanisms, DCA effectively captures both local and global dependencies within a long sequence, leading to improved performance on various tasks. DCA's benefits extend beyond its effectiveness. The method seamlessly integrates with flash attention too, a technique known for its speed and memory efficiency. This allows DCA to achieve comparable GPU memory usage and inference speed to the original self-attention mechanism in LLMs like Llama, even when handling longer contexts. Successive chunk attention is a refinement of inter-chunk attention, ensuring that adjacent chunks are processed with a continuity that preserves the contextual relationship across chunk boundaries. DCA allows for extrapolating more than 8x the training length without the need for costly and time-consuming further training. By decomposing the attention computation for long sequences into chunk-based modules, DCA manages to effectively capture the relative positional information of tokens within the same chunk, intra-chunk, and across distinct chunks, inter-chunk, as well as integrate seamlessly with flash attention. In addition to its impressive extrapolation capability, DCA achieves performance on practical long-context tasks that is comparable to or even better than that of fine-tuned models. When compared with proprietary models, their training-free 70B model attains 94% of the performance of GPT 3.5-16K for Llama 270B. DCA has proven effective in extending the context window to 96K tokens for Llama 270B. This extension is achieved with only a minor increase of 0.56 ppl compared to its original performance at a 4K context length. By integrating DCA with existing long context models, the enhanced system maintains a 90% retrieval accuracy with an extended context length of up to 192K tokens.